This is video 1 for the Nuclei and Radioactivity unit. For this unit, I want you to be able to explain what radioactivity is. I want you to be able to use the linear hypothesis to predict cancer in a population, so that'd be our math learning goal. I want you to be able to explain how radiocarbon dating works, and finally explain what fission and fusion are. Getting started then, radioactivity. It's actually quite simple. It's simply the explosion of a nucleus within an atom. That's all radioactivity is. So what makes this explosion, important and fascinating is the enormous energy released. And usually this is going to be about 1,000,000 times greater than in chemical explosions for the same number of atoms. So that's a lot. So atoms themselves are very, very small. They're about 1/10 of a nanometer. So to put it into perspective, a human hair has a thickness of right around 125,000 atoms. So if you took 125,000 atoms and put them end to end, that's about how thick a human hair is. A red blood cell is about 40,000 atoms wide. Each atom then consists of a cloud of electrons with tiny, very, very tiny nucleus in the center. So the nucleus of an atom is right around 10 to the negative 13th centimeters. So it's about 100,000 times smaller than the atom itself. A good example, if you were to inflate an atom to the size of a football field, which is about 300 meters, the nucleus would be about the size of a mosquito. So the scientist who discovered many of these interesting facts would be Ernest Rutherford. And he was one who discovered that atoms are basically empty space. So after he discovered that atoms are practically empty, within 20 years, we then learned that the nucleus itself was made up of even smaller pieces, protons and neutrons. So for the protons, they weigh about 2,000 times more than the electrons. Now they have the same charge as an electron, but they're positive. So whereas an electron is a negative charge, a proton is a positive charge. Neutrons have nearly the same mass as a proton. However, they have no electric charge. The neutron itself is actually just slightly more massive than the proton. Going on with a little more review, elements and isotopes. So the number of protons an atom has, or a nucleus has, is called the atomic number. This number also indicates the number of electrons in the electron cloud. So using hydrogen as an example, it has 1 proton, so it has 1 electron, and its atomic number is 1. The nucleus of an atom consists primarily of protons and neutrons. Neutrons have no charge, so they do not change the atom's behavior. Well, at least not much. Neutrons do have mass and can make the nucleus heavier, though. So atoms of the same element, so the same atomic number, but with different numbers of neutrons, are called isotopes. So we can begin talking about something called heavy water. Now, to understand heavy water, you need to understand that there are 3 isotopes of hydrogen. There's protium, there's deuterium, and tritium. So the first one, protium, is simply what we consider hydrogen. It's got one proton and one electron. Deuterium is the next isotope. It has one proton, one neutron, and then one electron. And tritium has one proton, two neutrons, and one electron. So what heavy water is, if we remember water's chemical formula, dihydrogen monoxide, has two hydrogens and one oxygen. In heavy water, the hydrogens contain an extra neutron. So in other words, we're making water with either deuterium or tritium. And that makes it heavy. In this graphic here to the right, we can see that, under normal conditions for water, 1 liter has a mass of 1 kilogram. Heavy water, it only takes 0.9 liters to make 1 kilogram. So it is a substantial difference. Now, heavy water itself is very important. It was very important during World War II in the development of nuclear reactors. Hitler had a special plant to purify deuterium. And, this was such a big fact that the Allies had to send in a team to blow that plant up. Now, going on with this isotopes, when it comes to radioactive elements like uranium, 99% of the uranium found in the Earth has a nucleus with 92 protons and 146 neutrons. We call this uranium-238. About 0.7% of this uranium has only 143 neutrons. That makes it uranium-235. And again, since both of these have 92 protons and 92 electrons, they have pretty close to the same chemical properties. So both of these isotopes react similarly with elements like oxygen and water. However, we're interested in the properties of their nucleus, specifically when we talk about the nuclear explosions. And the difference in uranium-235 and uranium-238, those differences in neutrons become very, very important. So let's get started with radiation and rays. The most common type of radioactivity happens in which a small particle is thrown out from a big nucleus that speeds close to the speed of light. So Henry Becquerel first discovered this in 1896. Something was being emitted from certain elements that would pass through certain materials and then get exposed on film. Now these were first called rays, and we have to remember that they did not know that these were actually particles. They thought they were rays. And these particles, or these rays, had similar properties to X-rays. And these X-rays were discovered a year earlier by Roentgen when he was working with certain types of materials. Now, the different kinds of rays, when they were discovered, were named after letters of the Greek alphabet. So we had alpha, beta, gamma, and then delta rays. And the way we classify them is by how far they penetrated into different materials, or what materials could stop them. So alpha rays could be stopped by paper. Beta rays could be stopped by wood. Gamma rays could be stopped by concrete or lead. And then delta rays, they thought they were different, but it turns out that delta rays simply were low energy beta rays. So they could be stopped by thicker materials like wood as well. So again, what it turned out was that these were not rays at all, but particles. So the alpha ray turned out to be a particle that had 2 neutrons and 2 protons. So really, if you think about it, that is the nucleus of a helium atom. Beta rays turned out to be electrons. Now there are 2 types of beta rays, positrons and electrons. Positrons are like electrons, are the same size and mass, but they have a positive charge. Gamma rays, well, these ones actually did turn out to be rays. These are high energy electromagnetic waves. So those were, these 3 are mainly the 3 forms of radiation that we know about: alpha rays, beta rays, and gamma rays, which are alpha and beta are actually particles, and not rays. So the old terminology has changed. Instead of saying rays, we now say radiation. So what radioactivity is the explosion of atomic nuclei. Radiation, then, is the pieces that get thrown out in that explosion. So each ray, or I should say each particle, is like a tiny little bullet. It's so tiny that you don't feel it if it hits you. In fact, alpha and beta rays, or alpha and beta particles, will bounce off of many of your atoms before they come to rest. Now, with each bounce, they can knock apart a molecule or mutate a gene. So the slowing bullet leaves a trail of damaged molecules in its wake. This damage is small, but if you get hit with a large number of these particles, the total effect can make you very ill or even kill you. Gamma rays, again, those gamma are the high energy electromagnetic waves. They tend to be absorbed by a single atom, so they frequently break up the atom or even its nucleus. So really what happens with gamma is that since it's breaking up atoms inside of your body, we get secondary radiation emitted. And it's that secondary radiation that causes the damage for gamma. All right, this will conclude video 1.